Ladies and gentlemen, welcome to our next presentation. We will get now an introduction to a new kind of development in measurement technology for the radiological evaluation of building structures. It's a great pleasure to have here one of the experts who is developing this kind of technology. Please welcome Timo Göhlich from Nuvia.
Hello and welcome. My name is Timo Göhlich from the company Nuvia Instruments. Today I would like to give you a presentation about radioactivity in building structures and how to measure it. Before we start, I would like to make you a little bit curious about what's technically possible. We see here a calibration stand and how a software in combination with the hardware can make radioactivity visible. The underlying system is called NuVision. But at this point, I do not want to give too much away. We'll take a closer look at the whole thing again later during the presentation. First, let's concentrate on the agenda of today's presentation, which is as follows. First, we will take a look at practice. Using the example of Mühleberg nuclear power plant from Switzerland, how the dismantling of so-called splinter protection stone works, and we have some nice pictures for you. And then we will go straight on to the practical side. Under point 2, we will also see some nice products with which you can really measure walls and ceilings. Also very important, point 3 and 4. There we will come back to the video from the beginning, and there I will show you how this new system, the NuVision, can be used to really capture measurement objects that may not have such a beautiful surface. Let's take a closer look at that right away. Point 5 does not really have anything to do with building structures, but I have broadened the topic a bit, and we will also look at how we can check storage casks for fuel elements for contamination. After we have dealt with ceilings and walls, the floors are still missing, of course. I would also like to present some very interesting systems with which large areas can be effectively checked for contamination. Well, let's start with the splinter protection stones. First of all, I would like to thank Sabrina Schellenberg from BKW, who kindly allowed me to use the following pictures in my presentation. Once again, many thanks. As you can see on the screen, the stones are arranged around the two turbines in the powerhouse of the NPP, where they provide mechanical protection for the turbines and, of course, the staff, if something should happen to the two powerful turbines. The good news first, the stones were not used throughout the operation of the power plant. On the next slides we will see how those stones are measured and how they are finally returned to the recycling cycle after a process of grinding and crushing. Here we see how the entire surface of the splinter protection stone is checked for radioactivity with the Kumo 170, which is a contamination detection device. Kumo 170 has a built-in plastic scintillation detector which reacts to alpha, beta and gamma radiation. On the right picture we can see very clearly how the worker proceeds. He marks the outlines of the Kumo 170, that is the 170 square centimeters, on the stone and can thus ensure that he measures all areas of the stone. In the next picture we see a similar procedure. The two gentlemen use a Kumo 300, that is a measuring device with a measuring surface of 300 square centimeters, and proceed very similarly to the example in Switzerland. They mark correspondingly the outlines of the Kumo 300 on the wall and can thus also ensure that all areas are measured. Here you can see even more clearly how the areas overlap and that no contamination is overlooked, even in the marginal area where no detector is present. For decommissioning, the Kumo 170G or 300G has become an established device. Those are devices which are equipped with a thick layer plastic scintillation detector and thus have a considerably higher efficiency for gamma ray nuclides. This is therefore very practical, very handy, especially if contaminations have already been painted over with decontamination paint several times. to really find contamination a little deeper in the structures. Other measuring methods have also been used in Mühleberg. Here we see a collimated detector which is placed in front of the stones to check again for gamma radiation. You can see beautifully on the left picture, you see the border of the Kumo 170 where every last angle has been measured. It was paid attention to it. And of course the whole thing can be documented again by this lining. This is shown here very nicely. At the bottom right we see how the stones are loaded, and at the top right how they are finally transported away. To close the recycling loop, however, there are still some steps missing in the work process. We can see this here on the next slide. The stones here have been broken into large pieces. You can see the border of Kumo 170 again, and in further work steps, small granules are made from these big concrete blocks. In this cycle, cement is produced in several steps from the remains, which is a binding agent for concrete. And we see here, for example, what's built from this concrete, that it is a tropical house, which is quite impressive. And so the recycling cycle closes accordingly. The advantage of the Kumo 170 or 300 is the flexible application possibilities, but there are also bigger systems like the PL525 detector system, which has a much bigger detector built in and which is shielded with lead or steel to increase the efficiency degree as opposed to the Kumo 170 or 300 in the gamma version. Here we see the system. It weighs a lot with the shielding. This means that larger areas should not be ironed manually, but should really have the help of a mechanical system. Here we see a manual mechanism for measuring ceilings or walls or door frames. This is especially suitable for smaller building parts that you want to measure, or if you want to have a bigger one, you can also use an electrical support to move the detector system. It is also possible to move the detector system from left to right, from top to bottom, and to install it in the ceiling to detect contamination. We can now take this even one step further by combining the detector system with the 525 and an automatic milling machine. The trick here is that you can switch it over here and fill the removed surface in a container for contaminated surface, and once again in another container for values below the exemption limit or the clearance limit. It is therefore a very smart system in order to remove large areas quickly. Let's take a look at some more details of how the system works. It's really an interesting thing to really move on with the dismantling. You don't have to reinvent the wheel every time, have you? Let's now come to a topic that has less to do with normal measurement technology. We are now dealing with structures that are much more difficult to measure than straight surfaces, such as the crane system here. We also use a special system for this purpose, which is the New Vision Gamma camera. The interesting about this system is that it measures gamma radiation and combines the whole thing with an optical image and a spectrum. That means that we see what we measure, and the system even tells us which nuclide is present there. We cannot outsmart physics with this. It means a certain level of gamma radiation must always reach the camera. We have installed a ZZT detector in the front, which reacts to the gamma radiation accordingly. Let's have a quick look at the video from the beginning of the presentation. In the middle, we see the real-time image with 3 different beam sources. At the top left, we see the isotopes identified by the system. In other words, we once colored cesium-137 in blue, sodium 22 in red and cobalt 57 in orange, for example. The spectrum is shown at the top right. In a second video, we'll take a closer look at this. Let's now come back to the example of our crane system. In addition to the coloring of nuclides, the camera also has the possibility to identify and mark hotspots accordingly. And in the following picture, we can see quite clearly where the hotspots are in the crane facility. After decontamination, this also allows you to check the success accordingly without really having to stay too long near the hotspots. In this specific example, this has of course also led to a considerable dose rate reduction on the worker, which is of course only to be welcomed. Let's now talk about the second example. This is a copper pipe that protrudes from a wall. And also here we take our new vision to see if we have a hotspot here. And as it happens, the system has identified cesium-137, and in the band it has appeared here accordingly. You can see that in the top left corner we see the nuclide inserted, in this case cesium-137 in the middle. In the optical display we see the marking of a hotspot in the band of the tube and also a hint to the dose rate. In this case it was calculated on the camera due to the built-in laser distance meter. However, it's also possible to make a back calculation to the starting point of the source, which is of course a very interesting possibility the system has here. On the right side we see faded in the spectrum at 662 keV. We see the peak, which corresponds to cesium-137. Below this blue slider, with this we can limit the energy range to be analyzed. This allows the system to easily identify a nuclide more quickly. These gamma camera systems in this form or in a simple form have already become established in NPPs in France and also China, where they ensure that workers really do receive less dose than would otherwise have been the case with other measurement methods. Let us now turn to other measuring systems. These are tube detectors, which can be used to measure contamination within the tubes. We have different versions with different diameters. The upper three are equipped with the thin film plastic scintillation detector and the lower two with a thick film plastic scintillation detector. The upper three are suitable for alpha, beta, gamma, and the lower two for gamma measurements only. For the measurement, the detectors are inserted into the tubes. For this purpose, it is necessary to attach guiding elements to the detectors. We can see that here on this slide. So we can define the distance from the detector to the pipe. For alpha measurements, it's of course very important that we place the detector as close as possible to the outside area to be measured. Let us now turn to another measuring system, a so-called lantern detector. It has 4 measuring surfaces, each equipped with a plastic scintillation detector, a thin layer for alpha, beta, gamma measurements. And we see here how it is used to check the storage shafts for fuel elements for radioactive contamination. Another place that's difficult to reach for checking radioactivity are the corners. The Nuvi company has also developed a special corner detector for this purpose. Here in different formats, in order to be able to really penetrate into the last corner and exclude that there is radioactive contamination. Let us now turn to the final chapter. This is about floors, both indoors and outdoors. The measuring system is called LARS, Large Area Radiation Scanner. Here we use the combination of a speed meter with 2 large plastic scintillation detectors to detect even the smallest contaminations in outdoor areas or in outside areas. As the name suggests, the system is ideal for checking really large areas in a short time. If, in addition to gamma radiation, we also want to measure alpha and beta, we have again here our proven Kumo 170 or Kumo 300 system. Here you see the three different versions. On the left side, the model with 1 unit, in the middle with 2 units, and on the right side, the model with the 3 units. If you use the Kumo 300 accordingly here, you can of course iron or check large areas indoors and in flat outdoor areas quickly and safely in a relatively short time. If the underground is not quite as level as in this example, you can also use the Vision Gamma camera to quickly and easily detect a source in uneven terrain or in this demolition house here. In this example, our colleagues from the Czech Republic had hit a source in this demolition house and set up the Vision, and the system detected the source very easily and quickly. The same goes for the outside area, of course. For the area outside a building, systems as those from our colleagues in the UK are also suitable. Here you see a portable Anna J detector guided by 2 people. The worker on the left has, as you can see, a backpack on him where a GPS is installed accordingly. This way the readings can be combined with the GPS data. This enables a protocol to be drawn up afterwards, where the area is graphically displayed and combined with the measured values. If we now imagine the whole thing one size bigger, we get to measuring vehicles that are also capable of off-road use and which are equipped with thick film plastic scintillation detectors. Of course, they make the heart of every radiation protectionist beat faster when these vehicles can be used to check really huge areas for radioactivity in a short time. This concludes my presentation. Thank you very much for sticking it out until the end, until here. I hope you have been able to take away some ideas for your work practice, and if you have questions, just send me an email. I will gladly answer your questions. Thank you very much.